You've worked very hard in order to understand the linear equations and the different values and how you manipulate the different formulas. Now the application comes in. Where do you use this? You will probably find types of questions that deal with linear equation application on tests like the ACT, the SAT, your GED, the GRE if you're going into a graduate program. Entrance exams and standardized testing often have applications for the linear equations. So if you would flip your notes back to the attributes of the different shapes when we were doing the geometry area, I will also leave a link to the geometry part on this series of videos for you to refresh your memory. But this is exactly why I asked you to take the notes, so you have this in front of you and so you can think about what the equations for linear and what the equations for the geometry we're talking about, so you can put the two together to solve problems that come up on these different tests. Not to mention, during your actual classroom units on these, you're certainly going to have your end of the unit tests, and this is helpful information. So, in this area, I've put some of the geometric shapes onto the coordinate grid. It would be probable that your questions would ask you something about area and perimeter of these shapes, but we have no raw data, except for the fact that we do have coordinate points on the graph. So we could identify our coordinate points and then use perhaps a distance formula. If you used your distance formula for the sides of any of these shapes, you could answer questions on perimeter and area. If you were to prove that this was actually a right triangle, it certainly looks like it, and I've put it on the graph so you can see that it lines up with some of the squares. But if I tip them, like I did in this case, then we would have to, consider other ways of showing and proving that a right triangle would have slopes of these two lines, the base and the height, that would be perpendicular to each other. So these two slopes should have opposite reciprocal slopes. And using the endpoints, you could fit that into those formulas that talk about the slope and actually prove that these two lines are perpendicular. In this case, this looks like you have a right angle, but it's, well, maybe I just got that on there crooked. If I tilt it like this, well, then that kind of distorts this. I'm not sure if that's a right angle or not, but you can prove it with the ordered pairs and your slope formula. I know that this is not going to come out perpendicular. The slopes are not going to be opposite reciprocal, but it looks kind of close, like it might be. In this shape, however, we could take the slopes of the top line and the bottom line and see if those have parallel slopes. In other words, the same slope. We can apply that same reasoning to all of our shapes. The angles with perpendicular slopes, the slope of parallel sides. Here's another parallel side, we think. In our what looks like an equilateral triangle, we would probably use the distance formula to prove that all three of those sides are the same. In our square, we could do parallel sides, and also we could do perpendicular angles. You can also do distance formula on this to prove that the sides are the same distance, which, of course, 4 sides and 4 right angles is proof of a square. So that's what I'm talking about when you've got a situation where you've got limited amount of information. You need to start to think about those formulas and the attributes of the shape itself, perhaps you can marry those two and actually make some sense out of those questions that leave you stumped. And while we're on the topic of application of, when we were doing the systems of equations, where we were just finding the spot where the lines intersected to put the traffic light in there, we can also use that same idea whenever our problems are putting together two different features that overlap. For example, like a mixture problem, where you've got so many Brazil nuts combined with the peanuts in those mixture problems. Or you might have the situation where one bus starts out at a certain time and then a second bus starts out, but the miles per hour are different and all that. When do they arrive, or when do they overlap? One plane takes off from Chicago going west to Denver, and the other one takes off from San Francisco going to Denver. When will they overlap or pass each other or land? You see what I'm saying? Those are the types of problem situations that arise where you think about, oh, that's an intersecting point. Where will they meet each other? I might be able to use this tool. So your bag of tools have to have some understanding of what they do in order to put it with the proper situation.